When electrical equipment such as ballasts and heating coils are failing during generator testing, several factors could be at play. These components can be sensitive to power quality issues and voltage fluctuations. Firstly, consider the possibility of a neutral shift. During the transfer to emergency power, a loss of the neutral connection can create voltage imbalances. This can cause overvoltages on one or more phases, leading to premature failure of ballasts and heating coils. Generators themselves can sometimes generate harmonics. Harmonics are distortions in the voltage waveform that can negatively impact sensitive electronic devices. Ballasts and heating coils can be particularly susceptible to damage from harmonics. When the system switches to emergency power, large inrush currents can also occur. These high currents can stress and damage sensitive electrical components. Overvoltage transients are another potential cause. The act of transferring to emergency power might create an overvoltage transient, which can briefly spike the voltage beyond the rated capacity of the ballasts and heating coils. Poor grounding practices can contribute to the problem. Inadequate grounding allows stray currents to flow through the electrical system, potentially causing overvoltages on specific phases. To diagnose and resolve the issue, follow these troubleshooting steps. Firstly, verify the operation of the transfer switch. Make sure the transfer switch is functioning correctly and consistently maintaining a proper neutral connection during the transfer process. Secondly, monitor the voltage conditions. Use a power quality analyzer to observe voltage levels and waveforms before, during, and after the transfer to emergency power. This will help identify any voltage imbalances or harmonic distortions present. Thirdly, check for inrush currents. Measure the inrush currents that occur when switching to emergency power. Determine if these currents are excessive and contributing to the equipment failures. Fourthly, inspect the generator. Have the generator thoroughly inspected and tested to ensure it's producing clean power and not generating excessive harmonics. Fifthly, improve grounding if necessary. Verify that the electrical system is properly grounded. Identify and eliminate any sources of stray currents that may be present. Sixthly, install surge protection. Implement surge protection devices to safeguard sensitive electrical components from damaging overvoltage transient. There are additional considerations. The building owner needs to ensure that all transfer equipment is appropriately rated for the connected load and incorporate suitable protection features. Regular maintenance and testing of both the generator and the transfer switch are essential to prevent future problems. Furthermore, it's crucial to educate the building owner and the electrician about the potential risks involved when transferring to emergency power. This can help prevent future issues through better operational practices. To elaborate on neutral shifts, it's important to understand how voltage imbalances can arise. In a balanced three-phase system, the neutral conductor carries very little current. However, if the neutral connection is lost or compromised, the voltages on each phase can become unbalanced. This means that some phases may experience voltages significantly higher than their nominal values, while others may experience lower voltages. These overvoltages can quickly damage ballasts and heating coils, which are designed to operate within a specific voltage range. Harmonics, as mentioned earlier, are distortions of the pure sinusoidal voltage waveform. They are typically caused by nonlinear loads, such as electronic devices and some types of lighting. Generators can also produce harmonics, especially if they are not properly maintained or if they are operating under heavy load. Harmonics can cause a variety of problems, including overheating of electrical equipment, reduced power factor, and interference with communication systems. Inrush currents are another common cause of electrical equipment failures. When a motor or transformer is first energized, it draws a large amount of current for a brief period of time. This inrush current can be several times higher than the normal operating current. If the electrical system is not properly designed to handle these inrush currents, it can lead to voltage dips and equipment damage. Overvoltage transients can also occur when switching between power sources. These transients are brief spikes in voltage that can be caused by a variety of factors, including lightning strikes, switching surges, and capacitor switching. Overvoltage transients can damage sensitive electronic equipment, even if they only last for a few microseconds. Poor grounding practices can also contribute to electrical equipment failures. A properly grounded electrical system provides a low impedance path for fault currents to flow back to the source. This helps to protect equipment from damage in the event of a short circuit or ground fault. If the grounding system is inadequate, fault currents may flow through unintended paths, causing overvoltages and equipment damage. To summarize, there are several potential causes of ballast and heating coil failures when switching to emergency generator power. These include neutral shifts, harmonics, inrush currents, overvoltage transients, and poor grounding. By following the troubleshooting steps outlined above, you can identify the root cause of the problem and implement corrective actions to prevent future failures. Consider the type of transfer switch being used. A 3-pole transfer switch only switches the phase conductors, while a 4-pole transfer switch switches all phase conductors and the neutral. A 4-pole transfer switch is generally preferred for systems with sensitive electronic equipment, as it provides better isolation between the generator and the utility power source. When inspecting the generator, pay close attention to the condition of the voltage regulator and the automatic voltage regulator or AVR. These components are responsible for maintaining a stable voltage output from the generator. If the voltage regulator is not functioning properly, it can lead to voltage fluctuations and equipment damage. Also consider the load in the generator. Overloading the generator can cause it to produce excessive harmonics and voltage fluctuations. Make sure that the generator is properly sized for the connected load and that it is not being overloaded. In addition to the troubleshooting steps outlined above, it is also important to perform regular maintenance on the generator and the transfer switch. This includes inspecting the equipment for signs of wear and tear, tightening connections, and cleaning contacts. Regular maintenance can help to prevent problems before they occur. Here are some additional details to consider when investigating the causes of ballast and heating coil failures during generator testing. Firstly, examine the neutral grounding. Ensure the neutral is properly grounded both at the generator and the service entrance. An ungrounded or poorly grounded neutral can lead to significant voltage imbalances, especially under unbalanced load conditions. Secondly, analyze the load distribution. Evaluate the load distribution across the 3 phases. Uneven loading could cause voltage imbalances, which can stress ballasts and heating coils. Adjust the load distribution to balance the phases as much as possible. Thirdly, test the generator output. Use a power quality analyzer to measure the generator's output voltage frequency and total harmonic distortion or THD. High THD can indicate a problem with the generator's excitation system or the nonlinear loads connected to it. Fourthly, verify the transfer switch settings. Check the settings on the automatic transfer switch or ATS, such as the voltage and frequency thresholds. Incorrect settings can cause the ATS to transfer to the generator prematurely or to fail to transfer back to utility power when it should. Fifthly, investigate grounding impedance. Measure the impedance of the grounding system. High impedance can limit the flow of fault current, increasing the risk of equipment damage. Sixthly, inspect for loose connections. Carefully inspect all electrical connections in the system, including those at the generator, transfer switch, and distribution panels. Loose connections can cause voltage drops and arcing, which can damage equipment. Seventhly, assess the age and condition of the equipment. Older ballasts and heating coils may be more susceptible to failure, especially if they have been subjected to repeated stress from voltage fluctuations or harmonics. Consider replacing aging equipment with newer, more robust models. Eighthly, review the wiring practices. Check the wiring practices to ensure they comply with applicable electrical codes and standards. Improper wiring can create ground loops and other problems that could affect power quality. Ninthly, implement a preventative maintenance program. Establish a preventative maintenance program for the generator, transfer switch, and other critical electrical equipment. This program should include regular inspections, testing, and cleaning. Tenthly, consider using power conditioning equipment. In some cases, it may be necessary to install power conditioning equipment, such as voltage regulators or harmonic filters, to improve power quality and protect sensitive equipment.